Right, yesterday we were talking about the reflection of light, and we stopped at the law of reflection, right? The incident ray and the reflected ray, the normal, the angle of incidence, and the angle of reflection. And the law of reflection stating that the angle of reflection is equal to the angle of incidence, right? Uh, there's a brief mention in the text about real and virtual images. And so I'm going to share two videos on that topic, which will hopefully give a better explanation than what's given in the book. And also the fact that they are giving practical demonstration. So here we go.
All right, YouTube. Today we're sitting in my garage so that I can show you a misconception that a lot of people have with lenses. So when you do a ray tracing diagram, there's typically an object and an image. And people don't really understand the difference between a virtual and a real image. So I want to show you a real image today and a virtual image. And we're sitting in my garage to do that so that we can use the objects across the street. You see, light is coming in from the neighbor's Jeep and the neighbor's house through this lens, and there's an image. An image forms on the other side of this convex lens. Now the problem is light passes through this and an image forms over here, and people expect there to be some sort of a hologram, like Princess Leia saying, "Help me, Obi-Wan Kenobi," but there's not. But there is in fact an image here. And the issue is that image focuses at a particular point. Now, if I hold this lens near the wall, look right here. As I put the lens closer and closer to the wall, there comes a point where all that light focuses and we get an image on the wall. If the lens is too far away, it's out of focus. The light is passing through here, but it's out of focus. But when this is just the right distance away, this image forms. And that is what we call a real image. You'll see, it's inverted and it's smaller. You can do the math for that. You can see that in some of my other videos for convex lenses. But you'll see, what we have here is a real image. We say it's real because it can be projected onto a surface, or really it's real because the image is on the opposite side of the lens from the objects. In this case, the car that just drove by.
Right, I'm going to stop here and clarify that this is just like a mention of real and virtual images. They're mentioning lenses. It's not something we've done. That will come up later. So the next topic we'll be doing is refraction of light, and then that will be followed by lenses, right? And so we're going to talk about light rays passing through lenses and getting focused. That's right. So it will come later in detail. And the other thing, he said that a real image is inverted. So if you just notice over here, you can see that this car is upside down. The house across the street is actually upside down. You can see the sky, the little, like a bit of blue over here at the bottom of the image. The real images are actually inverted. They're upside down, right? And that's also what happens with the images that are forming on the retina of our eyes. The question is, then why do we see everything the right way up? And so our brain is able to process that real image and flip it around so that we see everything right side up. Okay, so just a bit of clarification over there as to what a real image is and some of its properties. And again, detail will come later.
Now, we can do the same thing with a mirror. So here's a mirror. This is a concave mirror. Now if I try to hold this up against the wall, it's just going to reflect the wall. Now if I hold this so that it's reflecting light off of what's outside, you'll notice there's nothing for this light to project onto, which is why we got a whiteboard. Come around over here. So you'll see, this mirror is projecting an image onto the whiteboard. We'd say that's a real image. That image appears on something we can project it onto. Now in the case of a mirror, a real image shows up on the same side of the mirror as the object. In this case, you've got the Jeep in the background and then the image of the Jeep sitting against the whiteboard. Now, the question comes up then, what's a virtual image? If a real image gets projected onto something, stay right where you are. Okay? Now you're looking at a virtual image of my wife trying to videotape this. Can you see you in there? Okay. So what you see is an image that appears as though it's somewhere back here. It appears as though there's a teeny tiny little wife inside my mirror that is recording everything. All right. And we can see a similar situation with a lens. If I take a concave lens and we look at this, you should be able to see a teeny tiny little Jeep living inside that lens. It's a virtual image. It doesn't project through so that the image shows up on the same side of the lens. It appears as though there's an image somewhere back here of this teeny tiny little Jeep living inside that lens. So, this has been the difference between a real and a virtual image in my garage. And on that note, that's all for now.
Right now, hopefully that introduction made some sense as to what a real and virtual image is, particularly what a virtual image is. So, right, virtual images are not something you come across, right, with cameras or your eye or something, right? So, they're something that you can commonly experience with mirrors every day, right? So, whenever you see a reflection of yourself, right, in a mirror or glass, and it seems as if there's another person standing, and the distance of you or the object seems to be as far away in the mirror as it is in real life, right? And so that is a virtual image because it's forming behind the mirror, which is not what actually happens in a real image. Here's another one.
Like the pictures which are taken from the front camera are also virtual image, no?
How are they virtual?
Like, they are not real images though. Like from the back.
You mean like the selfie camera?
Yeah.
They are real images.
Okay.
Right. The difference is, right, what you're seeing on screen is what the processor is processing and showing you. Otherwise, in like a standard camera, you're not able to see the image unless it's after it's processed or until after you put it into the computer, right? Or until after you have it printed out. So in a mobile phone, basically, or modern digital cameras, you're able to see the picture immediately, and just because you're able to see them on screen doesn't make them virtual, right? Because what's happening is light is entering the camera, and the same way it is being projected onto a sensor, and then that sensor is processing it and making it upright and everything, right? So what you're seeing is the end product, right? But the image itself that is forming through the lens onto the sensor of the camera is real.
Okay.
Right, so it's inverted and everything. Does that make sense?
Yeah.
All right, so here's another one. This is one that's just using light.
What's the difference between a real and a virtual image? So let me show you two lenses. This is a two-dimensional diverging lens. I have these light beams coming in here, and you notice that once they pass through, they diverge, right? Okay, now if I take another kind of lens, a two-dimensional converging lens, you'll notice that these rays come in, these light rays come in, and they all meet at that point right there. That's a focal point. It turns out that we can do the same thing with an actual image, and the difference between a real and a virtual image is a real image, the light rays actually cross at that point. So if you're on this side, it looks like that's the light source. Whereas a virtual image, it looks like these light rays cross back over here, but they don't actually cross, but the human eye can't tell the difference. So let's try an actual real image. Here is, I have a light source right here. See, it looks like that. It's an image. It's lit up, so it's easier to project. And I can take an actual converging lens, move this back a little bit, and put it in the right spot, get it in focus. This seems to be back a little bit more. but you can see the image that I'm projecting onto that screen. It's not perfectly in focus because I haven't gotten everything lined up just right, but you can imagine that there is some location, I just can't get it right here, where that will be in focus. That is an image on the screen, and that's a real image. You cannot do that. Here's a diverging lens. You cannot do that. It does not make an image on the screen.
Okay, and so very quickly, if we just go to the text and see what it has to say about it, let me just share that with you. All right, and so they give that same explanation. A real image is one which can be produced on a screen. A virtual image cannot be formed on a screen. So that's what, you know, both the videos mentioned. And right, the virtual image is produced that, you know, by rays that do not pass through the lens, or in this case a mirror. And so the image on a mirror is virtual, and they're reflected at the mirror and appears to you coming from behind the mirror, right? So this is an object, you're viewing it, and it seems to be as far away in the mirror as it is in real life. And that's because, as you know, the second video mentioned diverging rays. And so light, zoom in a bit, light from this object is hitting the mirror, it's being reflected, and as you can see, it's diverging, so it's spreading out. But if you just retrace it back into the mirror, you can see at a point which is equidistant and, you know, actually, like, you know, so sort of the same point up in the mirror is where they're converging over here. And so it seems to be inside the mirror when it's actually that's not what's happening. Okay, so they're labeled real rays and virtual rays, and so this is the object and this is the image, and it's a virtual image unlike an actual one, right? And so the properties of the image, of this image, a virtual image in a plane mirror, is it is as far behind the mirror as the object is in front, with the line joining the same points on object and image being perpendicular to the mirror. So right over here, the lines joining, they're perpendicular. The same size of the object. So in the real image, you saw that the image that was being projected onto the screen was actually smaller than the object itself, right? And so it could be perhaps bigger if it were a magnifying lens. So that's a different story, but you know, it's not the same size, right? It could be, but it depends on the kind of lens. In a mirror, right, it always appears to be the same size. And then, right, you've got the fact that it's a virtual image, and that's also what they've mentioned over here, right, in plane mirrors, and how, I mean, right, they're put to use in certain situations. You would want to, you know, sort of keep this in mind, because there can be questions, a 1-mark question perhaps in an exam, asking you to give a practical situation where mirrors are used. And so, right, for example, they mentioned that restaurants have large mirrors on a wall to make the room look larger because it's reflecting the entire room, so it seems twice as big as it actually is, right? Okay, so with that, hopefully that's somewhat clear, at least, is it?
Yeah, a little bit.
Okay, all right, so a little bit works for the time being. And so with that, let's go to the whiteboard and move on to the next chapter. All right, if there's anything obviously left unclear or anything that's not covered, that's given over here in the introductory mention, then obviously we will come back to it. All right, can you see the whiteboard?
Yeah.
Okay, so we have next chapter 3.2.2, which is refraction of light. right? And so, right, as we mentioned earlier, refraction in case of light and waves in general is the bending of light. Since we're talking about light, I'm going to mention light, or waves in general, when passing from one medium Alright, so the term used is medium, which means material. So in this case, in the case of light, there you'll normally be coming across three different media. There's air, there's glass, and there's water. Alright, so three different materials, they're called medium. So when passing from one medium to another, and so that is the definition of refraction. Okay, and so when light travels in straight lines, but when it's moving between different materials, when it's moving between different media, as soon as it hits the boundary, when light rays hit the boundary between different media, they bend depending on the medium's optical density. Optical density. What is optical density? How much can it refract? How much can it bend the light? Okay, so we're not talking about density as in mass per unit volume. That's not the density we're talking about, right? In those terms, the physical density of the object might be something else, right? We're talking about the optical density. So what effects is it having on the light, on the waves that are passing through, right? And so there are certain facts about refraction that I'll list over here. And the first is that if light is moving from, is when it's entering an optically denser medium, and so this is what you would expect to happen when light is going from air through glass. So light was traveling through air, which is optically less dense than glass. Glass is optically denser than air, right? Which means it is able to bend light more. And so when, right, which way it's moving, between which materials is light traveling, is going to have an effect on how it is being refracted, how the light ray is being bent. So when light enters an optically denser medium, right, at an angle, so not straight, but at an angle, right, it will bend towards the normal. All right, so remember the normal, right, is perpendicular, is a perpendicular line to the surface of the medium. Now I will share an illustration with you which will make this clear. Let me just first go over these. Next, right, if light is moving, if it's entering an optically less dense medium, for example, it is moving from glass to air, right, and so the light will be bent away from the normal. The ray of light will be bent away from the normal. The third thing, which might be a bit confusing to understand in words, is a ray emerging from a parallel sided block is parallel. So I will take you to the illustration to make this clear, to the ray entering, but is displaced sideways. Displaced meaning moved sideways. And finally, a ray traveling along the normal direction at the boundary right is not refracted. Okay, now to make sense of all of this, let's take a look at the illustration in the book. Right, and so this is what we want to take a look at. And so this is, giving everything very well. The first thing we have, right, identifying this is the incident ray. So the ray coming in is, right, called the incident ray, and the ray that is refracted is called the refracted ray, obviously. This is the normal, the dotted line, which is perpendicular to the surface, the boundary of the medium. And then the angle between the incident ray and the normal is called the angle of incidence. And the angle between the incident ray and the refracted ray is called the angle of refraction. Okay. Then the first law was when it's entering an optically dense medium. So in this case, it's moving from air to glass. And so the ray will be bent towards the normal. You can see that the angle of incidence is larger the angle of refraction in this case is smaller, right? So the ray has been bent and it's been bent towards the normal. So that's the first thing that's happened. You wanted, right? Then if you ignore this part, you just look at the refracted ray. Consider this as the incident ray. This is the ray coming in, and this is the boundary between glass and air. So there's air outside again, and it's moving outside, right? And so you've got the normal, you've got the incident ray. This is, in this case, this is the refracted ray or the second refracted ray, whatever helps you understand. And so when it's entering an optically less dense medium, so air is less optically less dense than glass, right? And so the thing to keep in mind is that the ray will be bent away from the normal, and you can see that the angle between the normal and this ray over here in the glass is smaller as compared to the angle that you would find between the refracted ray coming out and the normal. So that's a large angle. So the light ray is bending away from the normal, right? So that's the second thing we talked about. And so that whole thing has been illustrated here. The third thing they mention, right, is a ray emerging from a parallel sided block. So this is the parallel sided block, right? These two are parallel, right? These, because these are the sides that the ray is passing through. And so, right, they are parallel, and sorry, is parallel to the ray entering. So if you, right, parallel means that they are moving in the same direction, right, at the same angle. And so if you measure this, you take a look at this, and you take a look at the ray that was coming in initially, these are both parallel, they're moving in the same direction, right? They have the same angle, and right, but it is displaced sideways. So instead of the ray passing through, and then, for example, if I just sort of move my mouse over here, right, instead of coming out over here somewhere, right, it's not coming out over here somewhere, it's coming out down here. So it has been moved that much, right? And so this is the displacement they're talking about. Why? Because of all the bending that took place, right? All of the refraction. So it is still parallel, it's still moving in the same direction it was, right? The angle and the direction is the same, but the physical location has been moved sideways. It's been, in this case, it's been moved down from where it would have been if it was traveling straight through air. Does that make sense? Right. How much did you miss? Hello? Okay. And then finally it says that a light ray entering, moving through a different medium along the normal will not be refracted, right? So a ray traveling along the normal direction at the boundary is not refracted. And so this was, the normal is perpendicular to the surface of the medium, the boundary surface of the medium. And so the light ray, in this case, entering, moving from air to glass and then glass to air, is also moving perpendicularly to the surface of the mediums, to the media, sorry, plural. And when that happens, it won't be refracted. So in this case, you can see it's passing right through. There's no bending taking place, right? And so these are the four things that you need to keep in mind when you are dealing with refraction. Okay. Now moving back to the whiteboard. There we go. Okay, next up, what we want to talk about, right, is refractive index. So yeah, angle of refraction. The angle of refraction is the angle between the refracted ray and the normal to a surface, right? Just like the angle of incidence and the angle of reflection, it is the angle between the refracted ray and the normal to a surface. And with that, we're going to talk about something that is refractive index. Right, so the refractive index of different media is calculated, and what that basically is, it is the right ratio of the angle of incidence to the angle of refraction. Well, not a direct ratio of the sine, that's a trigonometric function, of the angle of incidence to the sine of the angle of refraction. And so it's given as, right, refractive index is given as n equals to sine I over sine r. Okay, so that is something to remember. Now, what is this all about? Right, this is because right, light is bending because the speed of light is changing when it's moving through the different media, right? So light is refracted because its speed changes when moving through different media. So media is plural for medium. And so an example, right, what's the speed of light? Speed of light in air. We talked about light being faster than sound, is 3 into 10 to the power 8 meters per second, right? Or 300,000 kilometers per second. Pretty fast. And the speed of light in glass is slower. So that's 2 into 10 to the power 8. And that is significantly slower. Right? That's only, oh, sorry, we don't want the brackets here. It's only 200,000 kilometers per second. So 100,000 kilometers per second slower, which is a lot. Right? And so when that difference, right, occurs, right, that is what's causing, so that's what the optical density is about, right? The optical density is about how fast light is able to travel through a particular medium. If it's the same, you probably won't be noticing refraction happening, right? If two media have the same optical density. If, right, there is a difference, however slightly so, then you will notice some bending at least, right? And the video I believe we saw yesterday, uh, which talked about refraction and diffraction, all of that, right? It showed it, right, how the light was bending away from the mark he had made on the paper. So the greater the refractive index of a medium means the more the light is bent, right? And because this is the basis of refraction, right? The refractive index is unique to each medium. And so you can, right, you probably have these known values, and you can also, you'll probably be asked to calculate them in your exam paper. They'll give you a situation where light is passing through two media, and then to, first measure the angles of incidence and angles of refraction, then to find the refractive index of the media. And so the greater the refractive index of a medium, uh, right, the more the light is bent. Is that clear?
Yeah.
Okay. Right. And so something I sort of skipped, right? The entire explanation in the introductory chapter with water waves, right? So they explained refraction and diffraction, and right, with using water waves. And so in case of water waves, what they did was to show diffraction is they compared how water travels. I'm putting an asterisk over here. And so, for example, this is the bed, and then right over here, and right, this is water. So the height, right, so this is water, right, it's traveling, and the distance, so this is deep, so to speak, and this is obviously shallow. And so when water is moving, right, and the depth of the water changes, right, uh, its speed changes, and is also refracted. So, right, although we already know this, but experimentally, when they were studying this, they saw, well, okay, so we saw that, right, the speed of the water changes. How does it change? Water travels faster in when it's deeper, and slower when shallow. Right, so the waves of the water that are closer to the beach are actually slower as compared to the speed of the waves in deeper water, right? And so, right, when they noticed this, they saw, okay, not only is the speed changing when it's going from deep to shallow water, or vice versa, right? So going from deep to shallow is going to slow down, going from shallow to deep is going to speed up. And when that happens, the direction also changes. So the right, they were refracted. And when they noticed the same thing happening with light moving from, one medium to the other, and the speed changing, and along with the speed the light being bent, and so they thought, oh, so it's possible that light also has properties of waves. So that means light has something to do with waves. Maybe light is waves, right? Today we know that as a fact. But when it was being studied, that was a eureka movement, right? Like, the bulb just went on. Oh, so perhaps that's what it is. Okay. Now I had prepared for this all the way to the end, and I don't think there's a lot left with this chapter. Yeah, there isn't. But unfortunately, we are just about out of time. So, right, I don't think I'll be able to cover critical angle properly, and so I'll leave that for next time. How does that sound?
That's fine.
Okay. So yeah,
Yeah.
right. So we'll continue this next time, inshallah. Any questions?
No.
Okay. Allah Hafiz.
Allah Hafiz.